So now we will look into the properties of relation. So basically we have three types of properties for relation. We have reflexive, we have symmetric, and we have transitive. So what is reflexive? So the definition for the reflexive is as this. R, the relation, is reflexive if and only if this pair contain the same element, and this pair is an element of a relation for every element A, where A is an element of A. Written symbolically, R is reflexive if and only if for all X is an element of universal. If for all X, if X is an element of universal, then the binary or the binary pair, the pair here, XX, will also be an element of relation. So these R1, R3, R4 are the examples of the relation which has property reflexive. So the easiest way to see the reflexive is by looking at the equal sign here. So in this case, for the first relation, A is less than equal to B. So meaning that when A is equal to B, let's say A is 1, then meaning that B also 1. So if you have this, then it shows that this pair here with this relation, it is reflexive. Same goes to the R3 because it contains the equality here, and similar as R4. Alright, so but for the R2, R5, R6, if you see here, for the R2 there is no equality. Alright, and R5, if let's say the A is 3, right, like in this example here, if let's say the B is equal to 1, then you will get the pair as 2, 1, right? So and this pair here, it is not as X, right? This pair. So obviously it is not a reflexive. Okay, and same goes to this one, the R6. Alright, for the symmetric, a definition of R, when it has a property symmetric, then we can say that R is symmetric if and only if the element of BA, okay, this pair, is an element of relation R whenever AB is also an element of relation R for all AB in AB is an element of A. So when we write this in symbol, then we will got as this. R is symmetric if and only if for all X, all Y. If XY is an element of R, then YX is an element of R. So you can imagine symmetric as for your face, let's say. So we can say that human face in general, we have a symmetric shape. So if you cut your head into two, then you can see that your left part and your right part are symmetric, right? The human face, okay, the human head, I mean. All right, so that is also what symmetric all about, right? So now R3, R4, R6 are the examples of the relation with the symmetric properties. So in this case, if you see here, if let's say in the first example, there is an equality here. If A equal to 1, then B also equal to 1, then we can say that it is a symmetric. Alright, and then the same goes to the R4 and also for the R6. Alright, so for the R6, if let's say the A is equal to 1 1, and then B is equal to 2, right? Then if we total up these two things, then we can get this as 3. So this actually fulfill criteria. And if let's say this is for 1 2, and then if let's say we have 2 1, all right, so 2 1 also will give us equal to 3. So because of this, then we can say that this relation is symmetric. Okay, because 1 2 equal to 3, 2 1 also equal to 3. So because of this, then we can say that R6 is symmetric. All right. Okay, so what about, okay, so R1, R2, and R5, these are not symmetric because if you look into here, if let's say, okay, there is no problem if A equal to 1 and B, because if you notice for the R1 here, okay, this sign, it has two meaning, right? One is less than and one is equal to. So there is no problem with the equal sign here, because it will help us to give to easily identify the symmetric. But do not forget, for the R1, it has less than here. So if you look into here, if let's say we have 3 less than 4, this is basically fulfilled, right? 3 less than 4 is correct, right? Because 3 is less than 4. But what happens if we take 4 less than 3? All right, so because remember, because this is the symmetry, the AB and BA must be in the R. So in this case, the AB is satisfied, but the BA is not satisfied. All right, because of the sign, the less than sign. Okay, so same goes to the R2, and also same goes to the R5. The same justification. All right. So now we will look into the transitive relations. So a relation R on a set A is called transitive if whenever AB in R and BC in R, then AC in R. So you can imagine you have this first pair, AB, all right, and then you also have BC also in the relation. Alright, okay, so if this is happen, then AC must be an element of R2. So if this happen, then we can say that the relation is transitive. So if you look into the example here, alright, I will give you an example for the R1 here. Alright, so if let's say I take AB, okay, so let's say we take A equal to B, alright, because here it has A equal to B and A less than B. So we take one example here, A equal to B. Okay, sorry, we can take both actually, A less or equal to B. Alright, so if let's say we give some numbers here, let's say our AB here is 1 2. Alright, 1 2 here. Right, this is for our AB. And then our BC, so this is our A, our B, so our BC is 2. This is our B. This is our C. So it must fulfill this relation, right? So this one must be less than this one. Yeah, it must be less than this one. Let's say this one is 2 3. Alright, and then our AC in this case, because our A is 1 and our C is 3. So if you look into here, alright, if you look into here, our AB fulfill this condition. Our 2 3 also fulfill this condition. Our 1 3, our AC here also fulfill this condition, right? because the A here is less than the B or the C here. Alright, so that's why the R1 is transitive. Alright, so you can also repeat for the R2, R3 and R4. But for the R5, I can give you an example for this one. If let's say for the R5, yeah, let's say we have our A and our B here. If let's say our B, we take our B as 1 lah. Alright, as 1. So our A will be 1 plus 1 is equal to 2. And then our B, C here is, our B here is 1 now. So our C here will be 0. Okay, how I get 0? Because I may use this formula back. Okay, so for the B, for the BC, I have no the B here. So now this formula for the BC, this formula will become B equal to C plus 1. So in this case, our B is 1. So now we'll need to look for our C. So obviously our C is 0. Alright. So, and in this case, we will check. So our AC will be 2, 0. This is our AC. And if you look back in this case, if you try to plug in this value to check whether 2, 0 fulfill or not this relation, we can have this. Excuse me. So in this case, the A equal to C plus 1. And the A is 2 and the C is 0, so this one. So this is not equal, right? There is no way for the 2 to be equal to 1. Hence, the R5 is not transitive. You can check for the R6. You can use the same argument. Alright? Alright. So this is another example. It is very important when we talk about the properties, okay, of the relation. You must take into account all the elements in that specific set. For instance, let's say in this case, the relation R is on this set. Okay, that we give it a name as A. And this set A has an element 1, 2, 3. So for the reflexive property, you must highlight all the reflexive properties, and whatever you highlight, it must consist all element of this set. Okay, like in this example here, remember reflexive is when AA, the pair AA is an element of the relation, right? So in this case, if you notice here, we have 1, 1, this element, 2, 2, this one. How come this one, 2, 3? And we also have 3, 3 in this case. Alright, so since that it has fulfilled all the elements in this set, so we can say that this relation is reflexive. Right? So we look into the symmetric. The relation R on 1, 2, 3 is given by this. So let's check together. So symmetric is when XY in R, right? Then YX in R. Alright, so in this case, we have 1, 1. Alright, 1, 1, 1, 1. Okay, and then we have 1, 2. Alright, and we also have 2, 1. Okay, remember this one, xy, yx, so 1, 2, 2, 1. And then we have 1, 3, and we have 3, 1. So since that we have all this, then we can say that this relation is symmetric. Alright. Okay. So transitive. So this is, again, we use the same set here. So the transitive is when AB and pair BC, then AC. Right? AC. Okay, so let's check. So let's say we have 1, 1, and then we have 1, 2. So we will have 1, 2 again. So AB, BC, AC, right? 1, 1, 1, 2, and then 1, 2. And then we have next, we have 1, 2, 2, 1, and then we have 1, 1 here. So this is AB, BC, AC. Next we have 2, 2. We have 2, 2, 2, 1. Then we have 2, 1. So AB, BC, AC. Alright. And then next, we have 2, 2, 2, 3. And we have 1, 3. So it looks like we have all the elements. So we can say that this relation is transitive. Alright. So now, we will move into the directed graph of a relation. But let me see first. Yes, I think I can just proceed with this one. When a relation R is defined on a set A, the arrow diagram of the relation can be modified so that it becomes a directed graph. Instead of representing A as two separate sets of points, represent A only once and draw an arrow from each point of A to each related point, as with an ordinary arrow diagram. So for all points A at X and Y in A, there is an arrow from X to Y if and only if X is a relation of Y. Hence, this pair XY is in R. If a point is related to itself, a loop drawn that extends out from the point goes back to it. Right, so this is the example here. Let A with this element 3, 4, 5, 6, 7, 8 and define a relation R on A as follows for all X, Y in A. So X relation with Y is defined by this relation. A divides X minus Y. So draw the directed graph of R. So first thing first, you need to find the pair of this relation. So in this case, so 2 divides, so 3 minus 3, 0. So you will get 0, fine. And then this one you will get 1, right? So 5 minus 3, 2, so 1. This is 0, this is 1. This is, I believe, 7 minus 3 is 4, so this is 2. This is again 0. And then this one will be minus 2, so you will get minus 1. This one, minus 4. So this one is minus 2. And this one is 2. This is 1. This is 0. This is minus 1. So this is 1. This is 0. This is minus 1. This one is 7. This one is 2. This one is 1. This one is 0. This one 8 minus 4 from 4 over 2. So 2. This one is 1. This one is 0. Right. So in this case, if you notice, we have 1, 2, 3, 4, 5, 6. So we have 6 points. So we have 3 elements here. 3, 4, 5, 6, 7, and 8. So we have 3, 3. So this is what we call as directed graph. So this is 3. So meaning that it loops with itself, right? So 3, 3. 3, 5, let's say 3 is going to 5. This is 5, so 3 is going to 5. And then 3 is going to 7. And then 4. 4, it has it looping to itself. And then 4 is going to 6. 4 is going to 8. And then 5. 5 going to 3. 5 to itself. 5 to 7. 6, 4. 6 going to 4. 6 to itself. 6 to 8. 7 going to 3. 7 to 5. 7 to itself. 8, 4, and then 8, 6, and then 8 to itself. So this is what we call as directed graph. N-ary relation. N-ary relation form the mathematical foundation for relational database theory. A binary relation is a subset of a Cartesian product of two sets. Similarly, n-ary relation is a subset of Cartesian product of n sets. So just now, because we only play with two sets, so that's why we have to pair, right? So if let's say we have n-ary relations, let's say we have 3 tertiary relation, so we will have X, Y, and Z relation. Okay? Alright. Same goes if let's say we have 4, 3, then we have X, Y, Z, and alpha. Alright? So the special case of a ternary, triary, and fourary, we call it as ternary, binary, tertiary, and a quaternary relations. Alright. Example of n-ary relation. The following is a radically simplified version of database that might be used in the hospital. Let A1 be a positive integers, A2 set of alphabetic character strings, A3 is a set of numeric character strings, and A4 is a set of alphabetic character string. Define a quaternary relation R on A1, A2, A3, A4 as follows. So we have A1, A2, A3, A4. Remember, because now we have a product of 4 sets here. So automatically we will have 4 elements in this relation. So the first one is the ID, and then second is name. A2 is name, and then admitted date on A3. Primary diagnosis is on A4. At a particular hospital, this relation might contain the following quaternary or 4 tuples like this. Alright, so in discussions of relational database, the tuples are normally thought of as being written in table. Each row of the table corresponds to one tuple, and the header for each column describe the attribute. Like this one, this is the ID, this is the name, this is the admitted date, and this is the diagnosis. Right, so this is what it meant here. Right, so this is an example of the n-ary relation that you might use or when you learn the database. Alright, so next we will move into the equivalence relation in the next I still can just proceed. So for the equivalence relation, a relation on the set A is called equivalence if it is reflexive, symmetric, and transitive. If let's say that particular set, it has all this property, then we call that set, that relation of that set is equivalence. Okay, definition 2. Two elements A and B that are related by equivalence relation are called equivalent. The notation A with this, A with B is often used to denote that A and B are equivalent elements with respect to a particular equivalence relation. If the relation is equivalence, then the element also equivalence.